welcome you to the 103rd Game Changer seminar at ISI. I'm privileged to introduce today Dr. Fabio Crameri to you. Fabio graduated from the ETH in Zurich, Switzerland in 2013 with his PhD. He's subsequently been a researcher at the University College London and the University of Oslo on global scale convection of the Earth's mantle and other silica planets. Besides, Fabio developed several numerical models and image post-processing and graphic post-processing toolboxes. He developed concepts such as the ocean plate tectonics, and he also brought together earth scientists from different fields in a transdisciplinary fashion to build the subduction zone initiation database. He also developed a very interesting multi-metric for academic profile evaluation. Fabio created the open access graphics collection and designed the scientific color maps, all of which you can gain access to through the hyperlinks that are in the seminar announcement on ISI's website. 2020, Fabio founded his company Undertone Design for academic graphic design, and since the beginning of 2024, we at ISI are very happy to have him as our part-time communication specialist. Before I turn the floor to Fabio to give you a very, very interesting insight in seeing the unseen, accurate and inclusive color scales in space science, I would encourage all the colleagues on the call to kindly put their questions into the chat so that I can subsequently post them to Fabio, and if during the discussion afterwards there are some questions, I will then ask colleagues to raise their hands that we can give them the microphone. At this point in time, I'm very happy to have Fabio here to give us an interesting presentation on how to best use colors in scientific presentations and design. Fabio, the floor is yours. Glad that you're here today.
Thank you very much, Mike. So yeah, as Mike very kindly introduced, today we basically look at color and color in a scientific sense. So I think we all use color in our figures almost on a daily basis. So this is really about how to make this color use accurate and also inclusive for everyone throughout space sciences. So this is work I've done with my dear colleagues, Grace Shepard and Phil Heron. And we've published a paper. Well, now it's a couple of papers actually, but the main one is linked down there, and there's a QR code if you already want to have a look at it. This is basically an overview of what I will tell you today. So this whole initiative about a scientific color use very nicely aligns with ISI, you know, bringing together scientists, pushing the boundaries forward, making everything space science more inclusive to everyone. So I'm very happy I can be here and get this opportunity to talk to the space science audience. So let's get started. First, to motivate my talk, basically I want to tell you who you are. You're mostly, I guess, space scientists. And like any other scientists, you probably follow a scientific method. You start with a question, then make a hypothesis, then do some experiments, analyze them, try to understand them. And very often you go back to the beginning, start over again, etc., etc. But once you found something that is valuable to kind of put out there, you have to communicate it. And this is a very important step as a scientist. And unfortunately, these days, I think we spend not enough time to do that properly, because we really have to close this circle to make science work as a whole. So communication is done very effectively with visuals, and with that, with colors as well. Like on this slide, the colors really help to understand not only the slide, but also make it very intuitive to look at some information. So as a space scientist, you have a something you want to tell others, right? But if you turn the page now and think about the others, they have questions about space science. A big question, for example, would be this one here about the beginning of the universe. That happens a lot, especially after a few drinks. You start wondering, why is everything here and what do we know of it? So what they do is basically go these days to the internet. So maybe they have heard about the cosmic microwave background, one of the first observations we have of our universe. So they just Google it, and this is what pops up, Wikipedia, a reliable source. So you go in there, then you see this nice figure of the cosmic microwave background, but for them, it's basically just a figure and there's very little caption underneath it. So they click on it and it's basically just an oval with some color on it, which is basically meaningless to them. So then there's a link to go in deeper if they are curious enough to go there. And you get directed to the NASA webpage where this is explained in a bit more detail, but the figure remains just this oval with some colors on it. There's no scale on it, nothing. And even in the caption there, it only says that temperature fluctuation is shown as color differences, and the image shows a temperature range of plus minus 200 microkelvin. So that is really almost meaningless, right, to them, because you don't know whether the temperature range is shown between the blue colors and the yellow ones, or the green and the red ones, or whatever. So, and then if they're even still interested in this, they try to look for that actual data, which at least I couldn't find. So all they provide is the figures. And the figures are not very accessible at that. So in the best case, this is what happens. In the worst case, the person wondering is even color vision deficient, so it can't even see the red dots on this figure. So it all becomes yellow. So he or she loses the entire message of this figure. So they are left wondering about this very important and kind of, important question. That's my rather long introduction to why we are here today. We try to kind of do it better and make sure that the important space science that we do is brought out to everyone. So these are the learning goals for my talk. I will start with introducing what a color map is and then what a color bar is. That's not the same. I will introduce what a good color map is and what a bad color map is and how to differentiate them. We have to look at how we see colors and how others see colors. We don't all see the same colors. I will then go on and introduce what a scientific color map is, what different types of color maps there are, and how and when to use them. So I hope that will give you the tools to do better science in the end, and more accessible and more accurate. So color in science, there's two things to be aware of. First off, scientific visualization, usually with color, is a very common, if not the most common methodology in science. So almost any space scientist surely has used it before and uses it almost on a daily basis. At the same time, and that's a huge problem as it turns out, is that none of us has ever received in-depth education in scientific visualization, which is kind of mind-blowing if you think about it. So that's why I'm here, I guess, and that's why we had to write this paper and try to educate everyone kind of retrospectively. So for color in science, we have to differentiate between decoration and color used as an information carrier. And this is very important to differentiate and not to mix. So while decoration is kind of up to anyone's opinion, if you use color as an information carrier, it becomes very important that you do it right. So these are examples of color as decoration. I really don't care whether your pillow is green or red or whatever color you prefer. The same for the mark, as the same for, you know, kids drawing. And the same for the cats. I mean, these are beautiful cats, but as it turns out, that's actually a kind of special cat. Its color, the fur, is not here for decoration, really. It's here for as an information carrier. As it turns out, on the parts of the body where the cat is kind of cold, it develops darker fur than on parts of the body that are warmer, where the fur becomes more whitish. So the cat is a literal heat map of itself. Maybe more serious, why do we use color in science at all, in terms of an information carrier? This is very helpful. If you think about a three-dimensional data set, it's really hard to visualize that, and we often display our figures on two-dimensional canvases, like in a paper or on screens like here. And then if you have a three-dimensional data set, it's really hard to see some data points in the back and really grasp the difference between each of the data points. So now we can use or convert that third dimension from a position axis to a color axis. And we can use that with a color map. And just like that, we reduce the entire plot to a 2D plot, which then can conveniently be shown on paper, on screens, etc. Now, to realize that the color map is just part of this color bar, which is an axis. And as such, it has to fulfill certain properties. If you think about, you know, a position axis like that, it wouldn't make sense to make an axis like this, would it? Actually, if you would try to kind of submit a paper with an axis like this on a graph, first of all, your co-authors would speak up and tell you you can't do that because that would distort the data. If it turns out that your co-authors didn't read your paper and you submit, then the editor would surely speak up. If the editor's on holiday as well, then maybe during peer review, the reviewers would very likely speak up, so you wouldn't be able to publish this. Well, as it turns out, this is the most commonly used axis, just represented as a position axis. That's a rainbow color map. And as with the position axis, where the position are squeezed and elongated, in this rainbow color map, you have the changes in colors that are squeezed and kind of enlarged. And this then strongly distorts the data. So this is visualized here. So a change in data of 1, between 1, 2, 4, and 5, 7, and 8 should look the same, but it doesn't. For example, the cyan to green difference looks much smaller than the orange to red one. Moreover, if you kind of use these data points from this color map and just put them randomly, it's really hard to reorder them again. So it's very unintuitive to use a scale like this. Instead, scales should be accurate, and for color scales, that means they should be perceptually even, as we see it. Like with the position axis, the differences between 1 and 2 should look the same as between 7 and 8. So here there's a scientific color map where you can see that the changes between these data points look the same as well. So it's an even color map. So the data distortion that you introduce with bad color maps obviously becomes only obvious if you know ahead of looking at it how it looks like. So we did this example where we chose some well-known objects like an apple, a photograph of Marie Curie, and a photograph of our planet. And we kind of visualized them or represented this data with a bad color map, the rainbow color map, and also with the science-proof color map, like Batlow in this case. And as you can see on the left-hand side, The apple looks really distorted. If you would zoom in on the bite of the apple, you wouldn't even recognize it's a bite. Whereas for the scientific color map below, the pictures and the data looks perfect as is. If you want another example, I can try to make this exercise. Since you are all space scientists, I guess you know what that is. This is again data visualized with the unscientific color map rainbow. I hope you see what it is, because it should be clear. So if you want to see it with a scientific color map, it looks like this. And as you now might recognize, it's a person and an earring. And it's not just one person, it's ISIS executive director, Antonella Nota's earring. And here are all the other directors of ISI, because we know how they look like. And so with the scientific color map, they are flawless. With the rainbow color map, they get distorted. And they're actually hard to recognize, aren't they? Even worse, if you look in the background, the hills, they lose a lot of detail. The mountains are hardly recognizable. And it's just, you introduce a lot of artificial boundaries to the data set. So, but why is that? Why do we see different colors along the spectrum differently? It has to do a lot with the whole apparatus of how we see as humans. So what matters here is the light source, the surrounding. This changes a lot what we see. Then the colored object, or the object that we perceive as colored, in front of a background, which matters, reflects the light to our eye lens, which hits in the back of our eyes, the cone cells, which then transmit the information through an optical nerve to an optical cortex. And only then we see an apple as orange. So there's like a lot of research has gone into that, more than 100 years. And these clever people come up with some perceptually uniform color spaces. That's just color spaces where that represent color in the way we see it in a linear fashion. This is kind of complicated. One of these is called CCAM02, UCS. But all you need to know here is that you can derive a color difference metric, delta E. And this is basically a number that tells you how much a difference between two individual colors is based on how you perceive it. This is very important, and based on that you can actually create perceptually uniform color maps, and you can also diagnose them. So the scientific color map below, as you can see, the delta E is plotted here. It has a flat line, which means that all neighboring colors have the same color difference to each other. When you plot the most used color map in science chat, you can see that the curve is hugely uneven, which means that in some areas of the color map, you see more difference to other areas. And actually it becomes quite clear if you look at the rainbow color map that the cyan part and the yellow part stand out most to your eyes. And these are the brightest parts, and they're neither in the center nor at the end of the color map, which is problematic. So this is all based on numbers, and thanks to that, you can also derive a visual error that is introduced by this color map across the range of the data you show. For the scientific color map, this is generally below 0.3 or so percentage of the range that you display with the color map. For chat and even worse ones, this can be well beyond 8%. And 8% of a data range that you show is likely the biggest error in your data set and the biggest error in your study. So I guess it makes sense to avoid that. Just to outline this a bit more clearly, you can represent a flat line with Petlow, which still looks more or less flat. And if it's represented with chat, then it would more like a wobbly graph than anything flat. So this is all based on numbers, and I hope it serves as a really important example. Another kind of example to show you the distortion of that you introduce with the color map is shown here. So this is just one data set. It doesn't change. All you change is the minimum extreme value of the color bar. So all you should see is an increase and a decrease of color contrast, but the data should always look the same. It doesn't for the rainbow color map. In the rainbow color map, so this is a data set for mental convection model. You see some hot plumes rising to the surface, but at some point in the rainbow slice there, they seem to disappear or change entirely. So you basically can plot whatever you want, which is obviously not the scientific way of doing it. Whereas with the scientific version, the data always looks the same. So it really represents the data and not some visual artifacts. So yeah, the message is to use scientific color maps to see your data and not some visual artifacts. So that's my point one. It's about scientific accuracy. So you need to represent data and not blindly interpret it, which is what you do with a bad color map. Then your readers can't judge what you actually plot, and you can't judge what you actually plot. That would be enough, right, to kind of change your methodology and use scientific color maps. I can even make more points. Another one would be accessibility. So we all want to represent our data to everyone, not just a few of us. So that's where we have to start thinking about color vision deficiency. Not all people see colors the same. Some can't see some colors, and very few can't see any colors. So here is two proteins that I recently visualized for a paper. At the bottom, you see Google's Turbo color map, which they introduced recently and have been widely included in all kinds of software. On top, you see the scientific color map Bedlow. And if you kind of simulate how other people's look at these with different color vision deficiencies, you can see that with the scientific color map Bedlow, the data always looks the same. The colors change a bit, but you can still read it very well from low values to high values. When you use this Turbo rainbow color map, you can see that all the different simulations of color vision deficiencies, they start to look different. And for example, as you can see between the blue blind and the red blind simulation, the data, to me at least, looks very different. So you start to distort the data a lot. And actually in most of these simulations, you start to repeat colors. So they can't differentiate a couple of these colors. And then of course in the black and white version, you start to repeat the endpoints as well. So it becomes useless. Another example is shown here. On the left, you see a red-green color map. On the right, you see a pink-green color map. And you can guess which ones are accessible. The one on the left is not. As you can see here, if you're green blind, you can't differentiate the two extreme values. Positive from negative becomes really hard. And the same for red blindness. And for blue blindness, this is okay. Whereas if you have the scientific color map BAM on the right-hand side, all the people can see it perfectly fine. And then again, you can make examples. Often people think the example on the left bottom is accessible because you see many different colors, but in turn, if you make the test and convert it to black and white, they all look almost the same. Whereas for the scientific Bedlow S categorical color map, you can see that the gray version is still kind of readable. So then a third point can be made about the intuitive representation of our data. We really want to represent data effectively so that we can speed up the knowledge transfer. And this can be done with colors as well, and it can be kind of inhibited. So color scale should be intuitive. How is that done? Usually by having an intuitive order of the colors. So you can order colors based on color or based on lightness. And if you try both of them with the chat color map, you can't order them properly. They're always wrong, in the wrong order. Whereas if you have a scientific color map like Betlow, they're always in the right order. So if you see individual points along this color map, individual data points, you can easily order them from low to high, etc. So that's very powerful. Let's summarize this first part. Betlow is perceptually uniform, Betlow is perceptually ordered, Betlow is color vision deficiency friendly and even readable in black and white, whereas unscientific color maps like Rainbow are not. So we should start to not use them anymore, I think, because we all want to communicate the data without distorting it as intuitively as possible and to as many readers as possible. So for that, I created an entire suite of scientific color map. They're all perceptually even and ordered. They're all friendly to color vision deficiencies. And you can even read them in black and white. On top of it, they contain all the different color map types and classes, which is important because we have different data sets we want to visualize effectively. They're compatible with your favorite software, I hope. Provide them in more than 20 different formats, which is also a bit insane, but it seems like every software wants a different format. They are also versioned and citable, so this is already version 8. I keep improving them, I keep adding new things, and I really listen to everyone out there, so keep writing me emails about what you need and want, and we include them. So there's many different color maps as you've seen. So how do you apply them? First of all, there's different gradient types. So there's sequential ones, diverging ones, multi-sequential ones, and cyclic ones. The sequential ones, like Betlow, you would use for monotonic data, like sequential data sets. An example is seismic hazard across the Earth. So you display hazard from 0 to 5, and you want a sequential color map to just show the increase in hazard. Then you have the diverging ones. They have a dedicated middle point, which is usually a 0 point, and then you have some extreme values which tend to be anomalies. For example, here, that's the annual global surface temperature anomalies over time. And as you can see, the cold periods are displayed in bright blue, whereas the hot periods are displayed in bright red. And you can always see kind of the middle point. Then there's some special color maps like the multi-sequential ones, which is basically just 2 sequential ones stacked on top of each other. These are only used for very specific data sets like the topography of a planet, for example, if you have a sea level. So you can actually see the bathymetry below sea level and then the land topography above sea level. And they should match each other. So you represent, the changes in topography equally, no matter whether it's below sea level or above. And finally, you have this special case, the cyclic color maps. So they have no start and no end. This is useful if you represent, for example, this circular data like INSAR data sets of ground motion or some kind of angular data sets like the direct direction of rivers or something like that on a map. And then if this wasn't enough already, there is also different palette types. So I just showed you continuous ones where you basically have as as many colors so that you can't see the differences anymore between the individual colors. So they appear continuous. What you can now do is kind of reduce the total number of colors within a color gradient, for example, to 10 different values here. And this is kind of useful if you want to pick individual values very clearly. So they're used widely. And then finally, there's also a categorical palette type, which basically is used to represent unordered data sets, for example, line plots or scatter plots. And I provide them, they're also inclusive and accurate, and I provide them with up to 100 different colors. Of course, the more lines you would want to show, the closer the colors become. But in theory, you could show 100 different data sets, and they're still somewhat recognizable. So since this is a bit complex, we have created this flow chart, and you can find them on sync.org. So on the top half of this flow chart, you just have input what data set you use, and then you go through all these questions and you find what gradient type and what palette types you should use with a given data set. The bottom part is for an expert use of color. It tells you basically what color combination you should choose. So whether a dark color ending of the color map should be for low values or for high values. This is very important because the background, as I mentioned previously, matters as well. So depending on whether you show your figure on a dark screen or on a light paper, this is kind of important. I try to outline this here. So background and matters, two words, and they seem to have different colors, but they have actually the same color. You're just tricked into thinking it's a different color, and it's because of the background, the gradient in the background. And this is actually also works with color very well. So again, the two words have the same color, but background looks more yellowish than matters, which looks more greenish. And it's just introduced by the background. So this is important for us scientists as well, because we tend to, use heat maps, for example, a lot. Here I outlined the problem. The two piles with the little black dot have the same value and the same color, but they might look different to you just because the top left one has a more brightish colors around it than the bottom right one. And so we are tricked into thinking it's different values, whereas they are not. So here the tip is basically to introduce a boundary, black or white boundary around the tiles, which help to kind of reduce this effect a little bit. In the best case, you just put the numbers on each tile. So let's do a little exercise to get to really learn how you should apply the color map. So again, here there's seismic hazard, sequential data set. So what you do is use a sequential color map as well. Hazard, is kind of, we intuitively think about hazard if something is red or yellowish. So here I chose a red color. And then we plot it on a light background. So I use a dark color end for high values. I do that because then the high values have the strongest contrast to the background and they stand out most. So in this case, I use the Bilbao color map, which nicely kind of represents this data set. You see the low hazard values, you see less, they're less obvious, and the high values, they really stand out. So if you would show this figure on a dark background, what you would see is basically the low values standing out and the high values are kind of hidden because they now have a lower contrast to the background. So here you should invert the lightness of your color bar, which is done here. So here I used a bet low K with a dark ending, and then the high values are really the bright red ones, which then stand out again. So then our data set looks perfectly fine again. So mind the background. Just another example. So this is a diverging color map. It's the geoid. What you can see is kind of two anomalies, and you want them to stand out most. So on a light background, you have the dark red and the dark blue for the most extreme values. And again, if you have a dark background, you kind of use a different color map. This is Berlin, where you have the 0 values, which are close to the background here in dark. And then the extreme values are again light with the most contrast to the background. So they also look super nice if you do it like that. So now now that you know how to apply them, you also want to know how to use them. As I said before, provide them for all kinds of softwares. If you want or don't know how to use them with any kind of software, just let me know and we find a way to import them. This really has been a community effort, so people help me a lot with creating all these formats and also with building them right into the best software packages. You can find all the details and step-by-step guides for all these softwares in the user guide, which I provide with the color maps. So if it's kind of easy to use the color maps, why don't we all use them? And over the years, I've got so many feedback, about people. They're always, scientists in general are on the defense always, because we have to kind of defend our work against reviewers, against everyone. And so we tend to become less open the longer we are scientists. So here are some of the comments I got, and yeah, these are just a few. So like believing that color maps show more, feeling that the rainbow color maps are better, they just like them better. You can show what you want, and the most common ones are traditional usage. It's just a default in my software, or everyone uses it. So you can group them, these kind of reactions. The first ones are just if someone is convinced about them, and then there's misconception about what they are here for. And then a very common one is just convenience. So how can we combat them? So conviction we can combat with containment, misconception by education, and convenience just by convenience. For example, we can contain the usage of bad color maps by commenting in peer reviews. That's our job, actually. Journal author guidelines should be put in place to kind of educate people, because we never got educated. Or we can wait for a new generation, because I hope at least that universities will start to teach scientific visualization. And then we just all have to educate each other. So showing, suggesting, reminding people. And then, I try hard to make it as easy as possible to use them. So make the color maps accessible, try to have them as software defaults and not just on scientific color maps. And in general, being a role model. And that's where you can jump in as well. So here are some examples, some resources you can use to do that. We just uploaded some scientific color use reminders. You can basically copy, paste this text if a paper that you review uses bad colors in figures. So it's very effective to do. We wrote an entire author guidelines for journals and have them included in a couple of journals already. The next one to include them will be Geodynamica, which is a new Diamond Open Access journal that will launch next year, and is actually for you as well, for most of you. It will also cover exoplanets. And then just by showing, suggesting, and reminding to your peers, that the scientific use of colors is very important. And for that, we provided posters. If you don't want to speak to people directly, you can hang them up in coffee rooms or in printing rooms, or just leave them lie around somewhere. So yeah, it has become really a community effort because you can't, the usage of bad color maps is so ingrained in science and in scientists, it's really hard to change them. But we are on a good way. And now we can see different evolutions of different disciplines. So now I hope that the space science will also go forward with that. Yes, because it's part of our job and we want to do it as well as possible. Just to give you an example how it looks like currently in space science. So again, it's easy to do an internet image search for example, for Mars topography. This is what you see. It's basically our rainbow color map. That's actually the MOLA color map, which has been introduced and I think defined as a standard somewhere. And of course, everyone uses it. And because everyone uses it, more people use it. All the big names. And then you can see down here, there's one of me. Just try to kind of show that you don't have to use that. And it's actually better not to use it. Here are my reasons. I appreciate traditional usage of something, but in this case, it may be better to change it. Because if you show it like this, you start to miss craters. You make it look like there's water on Mars, whereas we don't know whether there is. You introduce artificial boundaries, you miss low amplitude features and have some unintuitive color coding. So the highest mountain peaks are in white, which is very counterintuitive. And then to go towards the end, I want to give you some other tips of using colors. So a general tip, and actually Maurizio Falanga, EASY director, just told me this morning that he actually likes to keep color to a minimum, and I can't agree more. And there's actually also some this person, Andy Kirk, that says gray is your best friend in data visualization, and it's probably true. We are now just given the opportunity to use color everywhere, but back in the days, you might remember papers with just black and white figures, and they can be very effective, and in most cases, they are more inclusive. So try to keep it to a minimum, but also know that color makes it easier to differentiate different data values. So you add more contrast to your data set, and you can refer to them, although you should be careful with that because you can refer to blue or the green part, but again, note that some people can't see these colors. And then color gradients can show variation in data more clearly, than just grayscales. If you want to highlight certain part of your data or ranges, you can't do that with a color map. This has been done many, many times. But you need to represent your data first, and it needs to be there to be judged by others as well. So if you start to fiddle around with the color map to interpret your data, you don't represent your data anymore, and then science becomes useless. So what you should do is just superpose, lines, contours, just draw on them. So it's clear that it's your interpretation and not some data feature. And then how do you spot a non-scientific color map? Usually it's quite easy. Often you see the individual colors along a color bar, as in this case here. So you see for the rainbow color map, the individual colors, they start to increase in contrast and lose contrast. So sometimes it's really hard to see the neighboring colors, which tells you that it's an uneven color gradient. Whereas if you look at Batlow on the right-hand side, you can see all neighboring colors have the same contrast. This is how it should be as a scale. If you want to test for accessibility, the simplest way is just to turn it into black and white. either just print it on a black and white printer, or most software tools have a desaturation toggle where you can just desaturate and then have a look at it. If it's still readable, then it's accessible to everyone who can see. Then it's not just the color use that matters. It's also important how you annotate your lines, for example, as is shown here. So again, if you in your figure caption write the green line, then note that this is not visible for all of your readers. So instead of having a legend somewhere outside of your plot, try to annotate all the graphs directly. Then you make sure everyone can understand the color-coded data. And of course, if you have lines, don't just use lines, you can use dashed lines and dotted lines to make it even more accessible. So in general, just try to reduce the dependency on color to understand your data. A very common mistake people make is to use diverging color maps, like here in the middle, for a sequential data set. So let's say this is a data set that increases from the bottom to the top. You want to show this with the color as well. If you use a diverging color map, then you introduce this central feature, which is here in white, which isn't part of your data set, but it looks like it would. So try not to do that. And then finally, if you want to use and share figures, do it with reliable sources. So an example is here, sync.org. That's an online collection of scientific figures that we put out on the internet, make them searchable, and also, just a way to share your science figures so that we can connect the people that are wondering to the actual sources, to the scientists themselves. On sync.org, we have different cool figures, such as a fully accessible table of elements. We have some animations of the Earth. We have animations of the topography of Antarctica with and without ice sheet. We have animations of sea surface temperature over the course of the year 2023, I guess it was. We have the different planets. We have all exoplanets that we know. We have the solar system on a postcard that you can give to your family. We have posters for your wall, for example, here, the evolution of the universe. We don't have the cosmic background radiation plot yet because I can't find the data, but I hope soon, maybe with the help of some of you, we can do that. Instead, we have some icons that you can use to remind your peers and about how bad unscientific color maps are for science. So I think I should stop soon. So this is just to wrap up. I had a look at space science during the last year. So these are some really nice examples that use scientific color maps. For example, in satellite observations, more remote sensing, beautifully Acton and La Jolla. Here you see all kinds of different scientific color maps for impact craters. This is the magnetosphere visualized with Nuke. You have visualizations of the moon in scientific color maps. Mars is represented with scientific color maps. Here you even have categorical color maps. So this plot is even readable in black and white. How cool is that? It's also Mars, then Venus. Again, Venus with more scientific color maps. On Mercury, Acton, it's a beautiful color map. The sun in the Davos color map. And even the stars here in Betlo K. And protostellar cores with the Matplotlib Inferno color map and Vic. Again, VIC for interstellar exploration. I think that was something like light sails. And then even cosmic gas and galaxies. And finally, intergalactic medium, represented by Viridis. So these are all scientific color maps. And so I would say the train has left the station, and let's make sure we're all on it and we move the field forward. So to conclude, what we learned, I hope, is that the color bar is a scale and it has to fulfill certain properties. You should use scientific color map because you don't want to distort your data, make it accessible. You can test your figures by converting them to black and white, then you know if they're accessible or not. Do remind your peers about color misuse. That's the most effective way to go forward from here. And be open for feedback. Teach your students now that you know all about that, and also teach your supervisors, why not? And then use and share your science grade graphics widely so that we can kind of spread them all across the internet. Again, all the color maps and information you find on my webpage. If you want to join the discussion on X or Blue Sky, I'm there as well, and also on LinkedIn. So I'm happy to take questions, and I would like to thank again to the International Space Science Institute for hosting this talk and having me and trying to improve the space science field with better colors. Thanks very much.
Thank you very much, Fabio, for this very interesting presentation and this new direction you took us into with representing scientific findings with color. We have quite some questions. Before we go into them, I'd like to remind colleagues on the call that this seminar has been recorded as a YouTube video. And if you follow our website, not only do you find the hyperlinks again that Fabio was just showing right now on our website, but you also find the link to the YouTube video should you want to recommend it to peers who couldn't be with us today, or would you like to revisit it? Now to the questions. There are quite some of them, and I have the first one from Enrique. It says the color maps are available for Python. Is there any specific library you are referring to on Python?
Yeah, so people have introduced different ones. I can't remember the names now, but there's at least 4 different implementation options. If you go to the user guide of the scientific color maps, it's step-by-step introduced which kind of color map, which kind of Python library are useful for you to use them.
Angie asked the question, it seems to me that these scientific color maps are also easier to use for printing, subtractive synthesis, as they contain fewer of these very vivid and very difficult to print colors. What's your experience in these cases?
Yeah, that's a good point. So if you print, the printer doesn't use the same kind of color representation as our screens do. So that can introduce some changes to the color, which is really hard to kind of control, I guess. But yeah, as you say, the very vivid colors there, they tend to be super hard to print properly. And the scientific color maps have more subtle kind of colors for different reasons. So yeah, I would agree that it's better.
Santiago asks, what is a good way to represent uncertainty in a map?
Uncertainty in a map? Never thought about that one. But maybe, yeah, ask your peers and just discuss it. And then sometimes you come up with ideas.
Right. Lindsay Smith asks, in the energy industry, some governing bodies request a particular rainbow format. Also, rainbows are the default in most proprietary software, as you had indicated, Fabio, because that's what's always been used. Is there a massive knowledge gap in applied geosciences on this topic? And from a survey this summer of the interns at the company I work for, only around 50% have covered this topic in their undergraduate degree, but 50% is better than none. I mean, it's more a statement than a question.
Yeah, as I said, the different disciplines, they are at different stages at the moment. And the most important reason why people use certain color maps is just convenience and what are the defaults in the most used software packages. So if these actually ask for rainbow type color maps, then it's really hard to not use them. But in that case, we need people to just speak up and go to the software developers, and the journals can do a lot by just having author guides, and in peer review, just mention if people can't publish bad color maps, which would make sense, then they will change it quickly. And actually, Lindsay Smith, who's here, I think as well, she did a great job in promoting it in these fields.
It was her question. So is there a two-dimensional analog of the uniform metric bat law, asks Damour.
Two-dimensional analog
of the uniform metric bat law.
I'm not sure I understand why metric. Bat law is just a color map.
Yeah, I wasn't sure to understand the question.
Okay. Otherwise, rephrase them.
Yeah. Okay, Lucrezia Pettinari is asking, is there a website or a place where I can test the color map that I've been using to see to what extent it complies with the requirements that you propose? Yeah,
so whether it's accessible, you can go to Coblis. I think it's colorblind simulator. Just Google it and you will find a couple of options. If you want to know whether it's perceptually uniform, then you need to I don't think there's a tool online to do that, but you might find some Python scripts online. I think, there is a couple of them available, and otherwise send it to me and I can run some diagnostics on it.
There's a comment from Lindsay again, which I quickly read. The main blocker of changing the default in my experience is the default in the software, which what we talked about. People using open source software like Python that uses a scientific color map by default data visualization is almost always good. When the default is a rainbow, people will use the rainbow. They assume it is fit for purpose. The other blocker is leadership, typically being the harder group to educate, as they have been used to rainbow visualization for longer. If they don't promote or request the change to accurate data visualization, it's hard to change a community from the bottom up. But I don't. You commented on that. And Jans Henke put Planck data of the cosmic microwave background into the chat. That may be interesting for you, Fabio. The hyperlink is there from Jans Henke in the middle of the comments. Jonathan Slavin, at least the matplotlib Python package has a perceptual uniform color map as a default. So thanks, Jonathan. That may be helpful for those who asked questions before. And there is an answer from Lindsay to Lucrezia. The webcap can test a color map in a format. And Lindsay, gives Lucrezia the hyperlink where you can test. So please look at the chat so that you find it. And Lucas Sorioso says that using a color oracle to simulate grayscale and various vision issues. And Royd Cyber asks, are your color maps available for the ideal software? I guess that's a question to you.
Not that I know of, but if you send me some example formats, I can provide that, unless it's kind of protected formats.
Yeah. There is DVG who says one can access the CMB data from Planck and gives an address in FITS format. Michael Zimmerman +1 to the folks who mentioned colorblindness tools. And Patrick Hannawald from DLR, he is sending at Lucrezia that there is a colorblind simulator. And thank you, Patrick, for giving the hyperlinks. Very important. So colleagues, please copy those links out of the chat right now. Colin Forsyth says, thank you for a very excellent talk. I read that in because it was really excellent, Fabio. So I wanted to
thank you.
Forward this praise. Congratulations. Could you share the presentation slides with us? This is up to you. People can see, as I said, the YouTube video, but I think you have to get in touch with Fabio individually, and you can do that through our websites, and I have to leave it up to him. And
I just shared some resources, yeah.
Okay, super. Thanks very much. James Solomon will change his rainbow habit in thanking you. And
That's a win.
Thierry, our fellow director, Thierry Dudok, as you said in the introduction, colors are mostly used to add one dimension to a map. There are some cases where we would like to add 2 dimensions, surface temperature and luminosity of stellar surface or concentration of their uncertainty are an example. Here we are with the uncertainties again. To what degree can we combine hue and luminance to achieve this?
Oh, now I understand, yeah. So you want to show 2 different kind of variables on it. I had a look at that quickly and kind of stopped afterwards, but I think it should be okay to do. The problem is, at least for my color maps, I use lightness as basically the backbone to make it accessible to everyone, so that you can also read it in black and white. So if you use lightness to show something and then hue to show something else, you kind of lose that kind of total accessibility of the color map. So yeah, you would have to make it less accessible to have this 2-dimensional way of using it.
Yeah, there are many more comments coming, many of them thanking you for the presentation, but Lindsay is also making a statement that you can install the Cramery library in Python. You can use all the color maps as you would any other matplotlib.com as well. Colors on paper, that's what Andrew Lasseritz asks. Colors on paper or photographs vary depending on lighting. Our eyes then try to correct to what is expected. For example, LED lights use combinations of spectral lines which may hide certain narrowband colors. It's more a statement than a question, but you may want to take issue with that.
Yeah, just that's a good point as well. So screens display colors a bit different, and I gave presentation on this topic as well on different occasions, and sometimes you have a really bad projector and then the colors are just all over the place. Yeah. So that's something you can't really take care of, but just to keep in mind.
2 more minor points. Patrick Hannawald is following up with the uncertainty question that we've been talking about before, and he's wondering if saturation could be a good factor to represent uncertainty. And not saturated colors could show very uncertain, bright colors could show low uncertainty, or does this introduce a perceptive problems? Question to you.
In theory, I think that should work. Yeah, you would try and have to see. I guess you would probably lose a bit of color contrast if you use them. Yeah, anyway, you have to look into it, and I would be interested to know. So let me know.
There's an interesting one from Armin who says, are you teaching the subject at Uni Bern for students?
Yeah, I would like to. So if you know someone who does the curriculum, let them know.
It seems that many other comments praise and thank you for raising that issue, because the wrong representation or wrong color presentation has bothered several colleagues on the call. And it's beyond the hour, and I want to thank you very, very much, Fabio, for an excellent topic which you covered expeditiously. And I'm sure the many colleagues on the call will carry that information further, which is important. And please consult the hyperlinks that were shared in the chat, but also those on Fabio's seminar announcement. Before I close, I want to thank all the colleagues to stay with us and asking interesting questions. And I want to point to our next seminar, which will take place on Thursday, the 26th of September, with Yuri Putanen on the imaging X-ray polarimetry explorer and the news thereof. And with that, thank you very much to the speaker. Thank you very much for the audience. And I wish you all a nice evening. And with that, the session is closed. Thanks. Have a good night.
Thank you. Bye-bye.